Well, hello, ladies and gentlemen. We're going to start our last topic for the course today, chemical reactions or combustion. So we haven't looked at how the individual species or components of a mixture, how they react or may react chemically to produce new components or species or chemicals. So that's what this last topic is going to be about for the course, chemical reactions. Now, today we're going to be doing basics and going over basic chemical reactions, so how we can keep track of molecules being produced or consumed during some sort of a reaction. So we're going to be going over basics today. We're going to start off with the most important thing you need to know when you're dealing with chemical reactions, which is called the reaction mechanism. The reaction mechanism is an equation which tells us the relationship between the inputs to the reaction and the outputs, or if you like, the reactants and the products. It tells us how the chemical reaction chemically proceeds from the initial state to the final state in theory. So the chemical reaction, the reaction mechanism is the means or the mechanism by which we produce products using reactants or inputs, okay? Then you've got the reaction and the reaction coordinate. The reaction equation, the reaction coordinate tell you how an actual reaction proceeds. It's different than the reaction mechanism. The reaction mechanism is the mechanism by which products are produced, and the reaction itself uses the reaction mechanism to predict how the chemistry goes. So there's a small difference between the reaction mechanism and the reaction. You'll see when we do the example. So as I said, we'll talk about the reaction mechanism, the reaction and the reaction coordinate, and we'll do an example to show how all these concepts are tied together. So let's get started here. Let's talk about what we mean by chemical reactions, sometimes called combustion. So let's say we have a closed system. Let's look at some examples here. We have a closed system, and we start at some initial state A. And this closed system originally contains some kind of a fuel and something that reacts with the fuel. So we will have a fuel plus an oxidizer. So a fuel plus an oxidizer. An oxidizer reacts with the fuel to release heat, et cetera, et cetera. Now, this fuel and oxidizer, this mixture of fuel and oxidizer is usually called the reactants. By the way, the fuel and oxidizer mixture could also include inert. So I'm going to write here, I can also include inert material. Inert material is material that doesn't participate in the reaction. It doesn't get changed chemically. A good example of that is nitrogen under most situations. Nitrogen, when you burn fuel with air, nitrogen really isn't converted to anything else, not in a significant way during the chemical reaction. So the reactants may include the fuel, the oxidizer, and any inert material. And then some sort of a spark occurs or some sort of trigger occurs, and we end up at a new state. We end up at a new state B, where we have products. Some chemistry has occurred, and the reactants have reacted, and we have some sort of products. So we have some sort of products of combustion or some sort of products of a chemical reaction. Examples here might be methane, CH4, plus air, which is a mixture of nitrogen and oxygen. You instigate a chemical reaction with some sort of a spark, and the product is water vapor, H2O, CO2, and nitrogen left over, okay? That would be an example of a closed system where we have some sort of chemical reaction going on. We also have open systems involving chemical reactions. Let's say we have a combustor here, some sort of an open system. that is used to burn some fuel in some kind of an oxidizer. So let's say in this port here, we have N dot fuel. So this is coming in at the inlets. The inlets I'm going to call location A. So we have N dot fuel at location A. So the reactants are all in the A state, if you like. And then we have N dot air. N dot air. So the left-hand side of this combustor, this duct, if you like, I'm going to call the left-hand side location A. In other words, the reactant side. So this is reactant side. Reactant side. Just like the reactant side on the closed system before we burn the fuel. And then we have some sort of a flame in here. So here's our flame. So on this side you have reactants, then you have a flame, and the reactants get burnt, the fuel gets oxidized by the oxidizer in the air, the oxygen, and we have products on the right. So over here we have reactants, over here we have products, and we have N dot products coming out. And the product side, I'm going to call location A. B, sorry. Reactant side is location A. Our fuel and oxidizer are on side A. They mix together and then they burn somewhere in this combustor, releasing heat perhaps. Maybe it's releasing heat. Who knows? Who knows? Releasing heat. And the result is some sort of product. So in the case, the fuel could be methane. Air, of course, has nitrogen and oxygen. The oxygen and methane react to produce H2O, CO2, and then there's some inert nitrogen that is also present in the products as well. So that's kind of what we're going to be looking at today. We're going to be looking at the thermal dynamics associated with combustion or chemical reactions. We'll mainly stick with open systems, probably exclusively stick with analyzing open systems. Combustors, so this is a combustor here. Its purpose is to release heat using a chemical reaction. So we'll be dealing with combustors as examples, open systems in this material, okay? All right, so let's talk a little bit about the reaction mechanism. So what is the reaction mechanism? The reaction mechanism is the mechanism or equation, if you like, that tells us how the chemistry, how the combustion occurs, how the chemistry reacts. So reaction mechanism. Hold on a minute. Sorry about that. So the reaction mechanism, it tells us the relationship between the products and the reactants. So it tells us how reactants and products are related. It tells us how the reactants and products are related. Okay, so let's talk about some rules here on reaction mechanism. There's some rules that you have to apply to build up this reaction mechanism. So rules. So number one, the reaction mechanism or chemical equation, if you like, reaction mechanism, all atomic elements must balance. So I'm going to write an equation here in a moment relating the products and the reactants, and atomically, in an atomic sense, the atoms must balance. It must be a chemically balanced equation. Number two, no inert atoms or molecules or components or species, if you like, no inert chemical components can be present. No inert chemical components can be present. We'll talk a little bit, we'll apply these rules here in just a moment. So let me show you what this equation looks like, this reaction mechanism that we're going to be doing. Let's do an example here. Let's say we have methane reacting with O2, oxygen, okay? So let me write down the chemical reaction here for the reaction or combustion of methane and oxygen. So we have 1 mole of CH4, that's methane, so methane CH4, plus some amount of O2, we'll figure it out in just a moment here, we can probably eyeball this one, produces a mole of CO2 plus 2 moles of H2O. Let's see here, the carbon balance for this equation, I should have 1 CO2 molecule for every molecule of methane. I should have 2 molecules of H2O for every 1 molecule of methane. And if I do the oxygen balance here, what? I have 2 O2. Okay, so that's the reaction mechanism for combustion of methane with oxygen. So let's look at our rules here. All atomic elements must balance. So the carbons are balanced, the hydrogen atoms are balanced, and the O2, let's see, I have 4 O atoms, and I have 2 here and 2 here. So 4 O atoms on both sides, not O2, O atoms on both sides of the equation. So this is atomically balanced. So that equation is atomically balanced. Then it says no inert chemical components can be present. I could write, let's say I'm burning methane with nitrogen and oxygen. So I could do 1 N2 here, 1 mole of N2, but N2 doesn't participate in the reaction. It's inert. So I have to also put 1 N2 on the product side. So this is the reactant side, and that's the product side. And notice that they cancel out. Notice that they cancel out. It doesn't participate in the reaction, so it cancels out in the reaction mechanism. So do not write your reaction mechanisms with inert material in there. Material that doesn't participate in the actual reaction. It doesn't burn. It doesn't change its chemical composition. Cancels out in the reaction mechanism. So don't write inert material in the reaction mechanism. So I want to point out here explicitly, we have 2 sides of the equation. We have the reactant side. That's what you start with, reactant side, and the product side. Reactant side and product side, okay? Now, these moles here, these moles that you see in front of all the various chemical components in the reaction mechanism, these tell us the mixture or the recipe for the chemical reaction. It's not the chemical reaction, but it's a recipe. It's a mechanism for the chemical reaction. These quantities here, these moles in front of the chemical elements, these are called stoichiometric coefficients. Stoichiometric coefficients. They give us the chemical recipe for the reaction. Let's make a table of these stoichiometric coefficients. Let's make a little table. So these guys here are all stoichiometric coefficients. So let's make a little table. I'm going to put the component here, chemical component. In this reaction, we have reaction mechanism, 4 different chemical components or species. Let me list them here. CH4, O2, CO2, and H2O. Now, I'm going to write these stoichiometric coefficients in the reaction mechanism. I'm going to write them up here in this column. Now, I'm going to give a symbol for these stoichiometric coefficients. So V sub I, these are the stoichiometric, stoichiometric coefficients. Stoichiometric coefficients. I'm going to write these numbers in front of my components in my reaction mechanism. Let's write the ones that are on the product side first. 1 and 2 for the CO and the H2O. 1 and 2. Those are my stoichiometric coefficients. Okay? On the product side. On the product side. Now, I'm going to write the coefficients in front of my chemical components. I'm going to write them for the reactant side here. I'm going to put a 1 and a 2, but I'm also going to put a negative sign here. Negative sign in front of the reactant side stoichiometric coefficients. So on the reactant side, these stoichiometric coefficients are negative, and on the product side, they are positive. So V sub I on the reactant side have a negative sign. Have a negative sign, and on the product side, these stoichiometric coefficients have a positive sign, okay? Positive sign. Positive sign, negative sign. Reactants, products, okay? So we have a list here of the stoichiometric coefficients for this chemical reaction. Methane with oxygen to produce CO2 and H2O. So this is a reaction mechanism for combustion of methane and oxygen, O2, to produce only CO2 and H2O. It's a recipe for how chemistry occurs with oxygen and methane reacting together. And the stoichiometric coefficients are listed in the table you see here, okay? Now, let's write an equation here. Let's say we have some chemical component. We have some chemical component. And I want to relate the amount of that chemical component in the reactant and in the products. So let's say here, so now we're going to talk about the actual reaction. The reaction, not the mechanism, the reaction. So let's say we have a container of reactants. So initially we have the number of moles of some chemical. Initially at state A. State A is the reactant mixture before the chemistry, before the reaction has occurred. And then, of course, something happens, a spark or something causes chemistry to take place, a chemical reaction. We end up at state B, and now we have products. So the composition of the products is the moles of each product component at B. So B refers to products, and A refers to reactants. So I want to know what the relationship is between the number of moles initially in the products for any species, I, and the number of moles in the products for any species, I. What's the relationship between the number of moles initially for some material or some chemical and the number of moles finally? How many moles of fuel are in the reactants? How many moles of fuel are in the products? How many moles of oxygen are in the reactions? How many moles of oxygen are in the products? So I want to know, well, for any species I or any component I, for any component I, the number of moles of the component I in the products is equal to the initial number of moles in the reactants plus the stoichiometric coefficient for that component times epsilon, where epsilon is a reaction coordinate. So this here is moles of chemical I in products. NIA is number of moles of chemical I in reactants. So the initial number of moles of chemical I, the final number of moles of chemical I is equal. So the final number of moles of chemical I is the initial number plus the stoichiometric coefficient. Stoichiometric coefficient for the chemical I times the reaction coordinate. So this epsilon is called the reaction coordinate. Reaction coordinate. It tells us how far the reaction goes chemically. It tells us how far the reaction moves chemically away from its initial state towards some final state. Okay? It's a way of keeping track of how far the reaction progresses. Okay? Now, this is a lot of talk here. Let's go through and do an example. Let's go do a proper example here. All right, ladies and gentlemen, let's do an example here. So we have complete combustion of butane. Butane is C4H10, complete combustion of butane in air. Air is composed of 21% O2 and 79% nitrogen. We're neglecting any trace gases, neglecting any moist air, so any H2O, it's just oxygen and nitrogen in air with the chemical composition that we see here, 21% O2, 79% nitrogen. That's the approximate composition of air. The products of combustion only include nitrogen, carbon dioxide, and H2O. That's all that's in the products. So we're adding just enough air to completely burn the fuel, the butane. So there's no fuel left over in the products, and there's no excess oxygen either. We're adding just enough fuel and no more, just enough air to the fuel and no more, just enough to oxidize or burn the butane. The mole flow rate, the rate at which we feed butane is 4 kmoles per second. So let me put up a schematic here. Let's put up our schematic here. We have a duct or a combustor, if you like. So we have the reactant side and the product side. There's a flame here. So we have m dot air going in on the reactant side. We have m dot of the fuel, which is C4H10. And that is on the reactant side. And then on the product side, so we have reactant. In other words, air plus fuel. The air includes nitrogen, that's inert. So, and then we have product. So we have a flame. Here's our flame. We have products, and the products will not include any butane. So N dot C4H10 on the product side is 0. N dot O2 on the product side is 0. So it says that the products only contain CO2, H2O, and any nitrogen. And then, of course, we have N dot CO2 on the product side. I don't know what that is. N dot H2O on the product side. I don't know what that is. And we have N dot nitrogen on the product side. I don't know what that is. Maybe we'll calculate them as we do the problem, okay? So what are we supposed to find here? We're supposed to find the reaction mechanism, the stoichiometric coefficients, find the actual reaction. In other words, the chemical formula with the flow rates in the chemical formula. Find the mole flow rate for the air at the inlet, and then calculate what's called the air-fuel ratio. The air-fuel ratio is the mole flow rate for the air divided by the mole flow rate for the fuel. That is air-fuel ratio with the bar over the top. Remember, properties in tables that have a bar over the top are on a per kilomole basis, and properties in tables which do not have a bar are on a per mass basis. So we're going to calculate the air-fuel ratio, N dot air over N dot fuel, on a mole basis, and we're also going to calculate it on a mass basis. These are easy to relate. You just need the molecular weight of the air and the fuel, and you can convert from one to the other, okay? All right, so let's get started here. Let's get started. Analysis. So let's calculate the reaction mechanism. Let's figure out what the reaction mechanism is. Well, I'm going to write a general reaction mechanism with non-inert components. And instead of putting coefficients in the equation, I'm going to put variables, symbols, okay? So we have on the reactant side, A times C4H10 plus B times O2. So butane and air and O2 react to form DCO2 plus EH2O. So this is our reaction mechanism without the coefficients. I just have variables in there. We're going to find out what A, B, D, and E are using atomic balances. All right? Now, I think I'm going to, first of all, get started by, we're going to do this reaction mechanism on a per kilomole of butane basis. So immediately I'm going to note, or I'm going to write, or say, set A equal 1. So I'm just going to set A equal to 1. I'm going to write the reaction mechanism on a per mole or kilomole basis of butane. Okay, so the first thing you do is set A equal to 1. Now I'm going to perform atomic balances. Atomic balance. Atomic balances. Let's do a carbon balance on this equation here. So a C balance, carbon. Well, I have 4 carbon atoms in the fuel. So I have 4 times, well, 1 times 4. I have no carbon in the O2. So I have B times 0. And that's equal to D times 1. 1 carbon atom per molecule of O2, and E times 0. There's no carbon in H2O, so plus E times 0. What does this imply here? Let's see here. These terms are gone. This implies D is equal to 4. D equal to 4. Okay, so immediately I can write D is equal to 4. So I got my stoichiometric coefficient for the CO2 now. How about for the hydrogen? Let's do the hydrogen, H. Hydrogen molecule, not H2, just single monotonic hydrogen. Let's see here, I have 1 times 10 plus B times 0, again, no hydrogen in the O2. And then I have no hydrogen in the CO2, so I have D times 0, and I have E times 2. There's 2 hydrogen atoms per H2O molecule, okay? So again, these are gone here, and I get E is equal to 5. E is equal to 5. Let's do an oxygen balance. Monotonic oxygen, not O2, monotonic oxygen. Well, I guess I better do an O2 here. I guess I better do an O2. Yeah, I'll do an O2 balance here. I'll do an O2 balance. That way I can get B. No, let's just do plain O. I think this is a better way to do it. Let's just do O. Monotonic oxygen. Okay, let's see here. I have B times 2. Well, let's first of all, 1 times 0. There's no oxygen in the fuel. Plus B times 2 equals D times 2 for the CO2 and E times 1. So that gives me B is equal to D plus E over 2. I know D and E, 4 and 5. So 4 plus 5 over 2, 6.5. So B is 6.5. So the stoichiometric equation for oxidation of butane is 1C4H10 plus 6.5 O2 becomes 4 CO2 plus 5 H2O. Let's tabulate the stoichiometric coefficients. Let's tabulate the stoichiometric coefficients. So, chemical component, stoichiometric coefficient, V sub I. Let's see here, I have 4 different chemical components in the mechanism. C4H10, O2, CO2, and H2O. 4 different chemical components in the reaction mechanism. Stoichiometric coefficients. A -1, this is the reactant side, that's the product side. So put a negative sign in front of the coefficients on the reactant side. -1, -6.5, +4, +5. Again, what's this negative and positive all about? The reactants are being consumed in the reaction. Therefore, they have negative signs in front of the coefficients. They are being consumed. The fuel and the oxygen are being burned to produce CO2 and H2O. So when you see a positive sign in front of the coefficients, that means those chemicals, those components are being produced. A negative sign, consumed when the reaction goes this way. A positive sign, components, chemicals are being produced when the reaction goes from left to right, okay? Okay, so we have the reaction mechanism. Let's put a little box around this thing. And there's our stoichiometric coefficients. So this is our reaction mechanism. That's our reaction mechanism. There we go. So I have my reaction mechanism. Check. And I have my stoichiometric coefficients. Let's get the reaction. We know that N dot for the fuel is 4 kilomoles per second into this thing. Let's get the reaction. Let's find out the actual relationship between inlet and outlet mole flow rates. 4 kilomoles per second. In fact, I'm going to write N dot C4, 4 kilomoles per second. I'm going to write it down here because I'm going to need it. Okay? Good. So I'm going to make a table, another table here. Another table. This is going to be a long table, so you might want to take a piece of paper and turn it sideways. Okay? I'm going to put the chemical components here. Oh, before I get going here, let's go back to the list of stoichiometric coefficients. I'm going to burn my butane in air. Air is oxygen plus nitrogen. So I technically have a fifth chemical. It's not in the reaction mechanism, but I do have a fifth chemical. It's nitrogen. So write N2 down here. Now, does nitrogen appear in the reaction mechanism? It does not, because it does not participate in the reaction. It is inert. We're going to assume here that the nitrogen doesn't burn in any way. We're not producing NOx or anything like that. So nitrogen is inert in this reaction. You don't see it in the equation because its coefficient, its stoichiometric coefficient is 0. You don't see it in the equation, so write down its stoichiometric coefficient as 0. Nitrogen is neither consumed nor produced in the reaction. That's why its stoichiometric coefficient is 0. It is inert. Inert. Doesn't chemically change. So it doesn't participate in the reaction. Okay, so let's make a little table here. Let's list all the chemicals, all the chemical components possible in our problem here, either on the product side or on the reactant side. So I have the butane, C4H10. I have the O2. I have the nitrogen, N2, I have the CO2, and I have the H2O. Okay, so 6 different chemicals, 5 different chemicals. Sorry, 1, 2, am I missing something? 1, 2, 3. Oh, no, hold on. Did I double up here? Yeah, 5, what am I thinking? 5 different chemicals. Sorry, brain is going to mush. Let's list the stoichiometric coefficients for these 5 chemicals. So V sub I, -1, -6.5. So these are consumed in the reaction, and we're producing CO2 and H2O, so 4 and 5. 4 and 5, and the nitrogen is not consumed or produced, doesn't participate, it's inert, so its stoichiometric coefficient is 0, it's inert. Now, let me write down, either based on the problem givens or something else maybe I know, let me write down the either known value or the symbol for the reactant. side mole flow rates. N dot I A. So what's the mole flow rates on the reactant side? So I know I got 4 kilomoles per second of the fuel coming in, the C4H10. So I'm going to write N dot C4H10 on the reactant side is equal to 4 kilomoles per second. Okay? That's a given in the problem statement. What's the mole flow rate on the reactant side for the O2? Well, it is 0.21 times N dot air. The air is 21% O2 and 79% nitrogen. So write 0.21 N dot air. The nitrogen is the remaining 79%. Here, I'll do this. N dot O2 on the reactant side is 0.21 N dot air. How about that? Okay. Yes, it's on the reactant side. What about for the nitrogen? So N dot N2 on the reactant side, A, is equal to 0.79 N dot air. And again, that's on the reactant side. Okay. Air is 79% N2, 21% O2. What about the CO2? Well, I'm told the air doesn't contain any CO2 and the fuel certainly doesn't. So N dot CO2 on the reactant side at the inlet is equal to 0. And so is the same for H2O. No H2O, no CO2 on the intake or reactant side. The flow is going this way. Okay. Okay, now I'm going to calculate, well, I'm going to write the formula and hopefully calculate what the mole flow rates are on the product side. N dot I on the product side. Now I'm going to write the equation here. I just wrote it up a moment ago when we defined the reaction coordinate. N dot IB is equal to the outlet flow rate for chemical component I is equal to the inlet flow rate of chemical component I plus the stoichiometric coefficient of chemical component I times the reaction coordinate. So I'm going to write the equation relating the inlet to the outlet, the reactant to the product side flow rates, and they're based on the stoichiometric coefficients and the reaction coordinate epsilon. Epsilon tells us how far the reaction goes, okay? All right, let's do the butane. So N dot C4H10 on the reactant side, on the product side, is equal to N dot C4H10 on the reactant side plus the stoichiometric coefficient. It's -1 times epsilon. Now, we're told in the problem statement that there is no fuel in the products. We completely burn the fuel. We add just enough oxygen and we completely burn the fuel. So N dot fuel at the product side is 0. Complete combustion of the fuel. Complete combustion of the fuel. That means, so this implies I can solve for epsilon, which is my reaction coordinate. Okay, put it over on the other side of the equation. I got a 1 there, so epsilon is equal to N dot C4H10 at the inlet, which is 4 kilomoles per second. So epsilon is 4 kilomoles per second. That's what the outlet condition of no excess fuel in the outlet gives me, okay? Now let's do the same thing for the oxygen. N dot O2 at the outlet is equal to N dot O2 at the inlet, the reactant side, plus the stoichiometric coefficient times reaction coordinate, epsilon. Now, there's no oxygen in the outlet, so N dot O2B is equal to 0. So this is gone. And I have N dot O2 at the inlet is equal to 6.5 times the reaction coordinate. So this implies N dot O2 at the inlet is equal to 6.5 times the reaction coordinate, or 6.5 times 4, that's 26 kilomoles per second. By the way, I can also get the flow rate for the air from this equation. How do I do that? Note, or I can write here, or, and I'm going to rewrite this equation right here. N dot O2 at the inlet is equal to 0.21. 0.21 N dot air at the inlet, and that's also equal to 6.5 times the reaction coordinate, epsilon. And this implies N dot air at the inlet. Let's see here. I got to take 4 times 6.5, which is 26. And I got to divide it by 0.21. 123 kilomoles per second. So that's N dot air flowing through on the reactant side. So N dot air, not a lot of room here. I think I'm going to move this. N dot air at the reactant side is 123, it's actually 123.8, by the way, kilomoles per second. Okay. I have N dot O2, but I also have N dot air. Okay. Let's see here, N dot N2. At the product side is equal to N dot N2 at the reactant side, plus the stoichiometric coefficient, 0, times the reaction coordinate. What does this imply? This means N dot N2 at the outlet, the product side, is equal to N dot N2 on the reactant side. Not consumed, no burning, it's inert. So N2 that flows in is equal to N2 that flows out. And again, I can calculate this here. Let's see here, this is 0.79 N dot air. Which is equal to 0.79 times 123.8 kilomoles per second. And I get 97, basically 98 kilomoles per second. 98 kilomoles per second. (98 kilomoles per second). 98 kilomoles per second. Okay? All right. Let's do the CO2. N dot CO2 in the product side is equal to N dot CO2 on the reactant side, plus the stoichiometric coefficient, which is 4, times the reaction coordinate. There is no CO2 in the reactant side. And so I get 4 times 4, epsilon is 4, so 16 kilomoles per second. And we'll do the H2O, N dot H2O at the outlet or the reactant side is equal to N dot H2O on the product side plus 5 times the reaction coordinate. Reaction coordinate is 4, so I get 20 kilomoles per second. 20 kilomoles per second. 20 kilomoles per second. 16 and 20, let's see here. 16 kilomoles per second, 20 kilomoles per second. Oh boy, not enough room to write. And for the nitrogen, 98 kilomoles per second. Okay, difficult to write. All right, let's write out the final reaction. Not the mechanism, the reaction. That's the reaction mechanism there. No inert stuff in there. I don't have any N dots. I just have coefficients. Let's write the actual reaction. Let's write the actual reaction as it occurs in this combustion chamber, burning 4 kilomoles of butane per second. So what's the actual reaction? The reaction. I'm going to write the chemicals with the various flow rates. Let's see here. 4 kilomole per second of C4H10 plus 123.8 kilomole per second. That's our airflow rate times 0.2102 plus 0.79 N2. So this guy here is my N dot for the air, okay? And of course, this is N dot for the O2, and this is N dot for the N2. And that reacts or burns to produce CO2, H2O, and nitrogen. So I get, how much nitrogen is in the outlet? 98 kilomoles per second of nitrogen plus 16 kilomoles per second of CO2 plus 20 kilomoles per second of H2O. This is our reaction mechanism. I'm sorry, reaction. Ugh. This is our reaction. Put a big box around it. Feel free to break it into 2 lines by putting a break where the arrow is. That's fine. But that is our reaction, complete with mole flow rates and chemicals. It tells us how this particular reaction proceeds with the various mole flow rates specified in the problem, okay? Specified in the problem. All right, so let's calculate the air-fuel ratio. Air-fuel bar. What is air-fuel ratio? Air is the mole flow rate of air divided by the mole flow rate of fuel in our problem. Of course, our fuel is butane. Let's see here. N dot for the air, 123.8 kilomoles of air per second. I'll put air here. And N dot fuel is 4 kilomoles per second, and that's for the fuel. That's our fuel. Oh, what's our air-fuel ratio? 123.8 divided by 4, and I get 30.9195, which is approximately equal to 31. So 31 kilomole air per kilomole fuel. So air fuel on a per mole basis is 31 kilomole of air per kilomole of fuel. That's our air-fuel ratio. It tells us how much air we have to mix in per unit fuel to achieve this chemical reaction in this problem, okay? What about air-fuel without the bar? So air-fuel without the bar is mass flow rate of air divided by mass flow rate of fuel. It'll have units of kilograms of air per kilogram of fuel. The time cancels out in the ratio, okay? Now I can get that pretty easily with the mole flow rate and the molecular weight for air and fuel. That's n dot air times the molecular weight of air over n dot fuel times the molecular weight of fuel. Notice that n dot air over n dot fuel is the air-fuel ratio on a per mole basis. So I get air-fuel ratio on a per mole basis times the ratio of the molecular weight for the air over the molecular weight for the fuel. Let's see here, our air-fuel ratio is 31 kilomoles air per kilomole fuel. And now I need the molecular weights for air and the fuel. Looking up in tables, the molecular weight for air is 28.97 and for the butane is 58.12. So 28.97, 28.97, 58.12. And I get an air-fuel ratio of 15.4. And the unit there is kilogram of air per kilogram of the butane fuel. So air-fuel ratio, 15.2, or kilogram of air per kilogram of fuel. Okay, there we go. There's our air-fuel ratios. All right, so this is what I presented here is a systematic way of determining a reaction. So the idea here is, first of all, you better know what your flow rates are. You better know what your givens are. You're kind of screwed. Then you need to develop the reaction mechanism. How do you develop the reaction mechanism? You apply atomic balances, and you follow the rules according to how a reaction mechanism should be developed. Reaction mechanism does not include inert, non-participating components. Then you write down the stoichiometric coefficients. The stoichiometric coefficients are the coefficients in the reaction mechanism where there are negative signs if the chemical components are on the reactant side and positive signs if they're on the product side. And then you use the simple equation relating reactant mole flow rates, product mole flow rates, the simple equation relating the two. So the difference between the product and the reactant flow rates is equal to the stoichiometric coefficient times the reaction coordinate epsilon. Very simple equation. And then you just do a bunch of accounting. It's just a bunch of brute force cranking away. Solve for the reaction mechanism, solve for the reaction coordinate epsilon at some point, and then solve for the various mole flow rates for the products and the reactants in due course. All right, ladies and gentlemen, I think we're going to stop it here. This has been a bit of a long lecture. Take care.